Now, something that's interesting about inertia also is that it affects all particles equally, in the sense that if you take any particle of any speed at any mass, at any whatever it might be, and you give it a certain speed in a certain direction, then it will continue, obviously, in that direction with that speed. That's the definition of inertia. In other words, it affects everything equally. You can't see what the mass of an object is by looking at an inertial particle on its own. It's just going to continue moving straight forever. We'll call this an equivalence principle. It deals equivalently with all different particles. Okay? Can you think of any other phenomena that affects all particles in the same way? The electric field, okay, if you look at the force that an electric field exerts on a particle, what is it proportional to? Charge mass ratio, E over m, right? Magnetic field and so on. What field is there in nature that interacts with all particles in the same way, just as inertia interacts with all particles in the same way?
Gravity.
Gravity. Okay? Right? And in fact, the word equivalence principle, usually it's used only for gravity, but I'm using it advisedly also for inertia, and you'll see later that we're going to combine the two. So we have another equivalence principle telling us that all particles are affected the same way. There's only one force which we know of which has this property that it's independent of the properties of the particle, whether it's the mass of the particle or the speed of the particle. In electricity and magnetism, of course, what does the force depend on? Charge and velocity. Could be like QV cross V, right? You've seen that. It could depend on Q or E over m, right? Because the acceleration will depend, the force might not depend on the mass, but the acceleration that results from the force will be the force over the mass. So the resulting acceleration will be E over m. All right, so it certainly does depend on the mass, and it could depend on the velocity. The only force that we know of which gives rise to an acceleration which is independent of the mass and of the velocity is gravity. And therefore, gravity, too, can be considered as a field on space plus time. Right? You have F is equal to gmm over r squared. A is F over m. You just divide by the m. You get A is equal to gm over r squared. It doesn't depend on the particle. It doesn't depend on the velocity. In other words, outside of spherical mass, for example, you can label each point in space with an amount equal to gm over r squared. And you just say whatever particle arrives at this point will have an acceleration of gm over r squared towards the center of the object. It doesn't matter how fast it was moving through that point. It doesn't matter at what speed it was moving through that point. You can have three particles, one moving this way, one moving that way, one moving this way. If they intersect at a point without crashing, at that point they all have exactly the same acceleration. One could be a huge mass, a small mass, fast speed, this direction, it doesn't matter. It's a field on space. So it doesn't depend at all on the properties of the thing that crosses through that point in space. Okay, so that's only true about inertia and about gravity. Now, we saw many parallels between inertia and gravity. For example, if you're in an elevator that's rising, the force that you feel, which is an inertial force, is not distinguishable from gravity. Okay, if you let something drop in a gravitational field and it accelerates down, that phenomenon is exactly the same as if you have a rocket or an elevator accelerating up towards something that's inertial. There'll be a relative acceleration between the two of you if the rocket is accelerating, or if you're just standing still and this thing is accelerating due to gravity. All right? But basically, inertia and gravity are the same thing. There's really no such thing as inertia, because wherever you go in the universe, there is a gravitational field. Why? Is there an electric field wherever you go necessarily in the universe? No, because electric fields can be shielded. Magnetic fields can be shielded because there's different charges. You have plus minus charges, you have ions, you have all kinds of things, molecules, atoms, right? They're somewhat charged. But as you go further out in scale, you don't feel those charges anymore. They balance out eventually. Right? Gravitationally, nothing can be shielded, and therefore, the more you have, the more gravitational field there is. Now, you can go far away, so you have r squared is large, and it gets smaller and smaller. But of course, the further away you go from something, you get closer to something else. And no matter how far away you go, you're not going to be infinite distance, so it's never going to be zero. So you cannot shield gravity, therefore there's no such thing as inertial motion. Wherever you are in the universe, you're being affected by a gravitational field. So really we can just junk the idea of inertia and just talk about gravity. There's a field, and it's equal to gm over r squared. Well, it's not really gm over r squared because there's so many masses affecting you, so it's not necessarily spherically symmetric. It depends on what scale you're at. But you figure out the gravitational field where you are, figure out the acceleration, and that gives you, if you're far enough away from masses and your measuring instruments are not strong enough, you might think that there's actually no gravitational field, and you'll call it inertial motion.